Hello, my name is Bridget Tenner, and I'm an associate professor of mathematics at DePaul University in Chicago. I'm going to talk to you today about a result called Pick's theorem. Pick's theorem is a geometry result about finding the area of certain kinds of shapes in the plane. So in order to tell you what Pick's theorem is, in order to state it at all, I first have to make a definition. Pick's theorem is about lattice polygons, so I must begin by telling you what a lattice point is. If you think about the coordinate plane, we identify points by two coordinates, x, comma, y. And you could have anything. You can have pi, comma, negative root 3. You can have 0, comma, 10. A lattice point is a point whose coordinates are both integers. So let me write that down for you. A lattice point is x comma y, where x and y are both integers. X and y are both integers. So if you had to think about what those would look like in the plane, they would identify a grid. So here is a grid. I have not drawn the axes, but you can see a lot of points, and this is what the lattice points would look like in the plane. And the axes themselves don't matter, so I just want to think about this grid. If you ever used a geoboard as a kid, where you had these nails in a board and you wrapped rubber bands around them, that's what you were looking at. A lattice polygon is a shape where the edges are straight lines and the vertices are all at lattice points. So let me draw a lattice polygon for you. So I want you to notice first that all the vertices are indeed at lattice points. All the edges are straight lines, or as straight as I can make them. And also that I've made kind of a funky shape. So you might normally think of convex shapes, but I did put some angles here that are non-convex. And Pick's theorem will allow us to compute the area of this star quite easily, in fact. If you don't have Pick's theorem at your disposal and you want to find the area, you might do something like cut this up into triangles or squares and rectangles whose area you can calculate very easily and then add those up. But Pick's theorem skips all that and we can do it directly. So let me tell you what Pick's theorem says. First, as you look at this picture, you notice that my vertices were at lattice points, but also some of the edges went through other lattice points, like right here and right here. And also that there were more lattice points on the interior of our shape. So for any polygon, any lattice polygon, I can count the number of lattice points on its boundary. We would call that B of the polygon. And I can count the number of lattice points on the interior, which I will call I for interior of the polygon. And Pick's theorem says that the area of the polygon can be computed from those two numbers as this. For any lattice polygon, and that's important, not any shape, but any lattice polygon, the area of the polygon is the number of lattice points on the interior plus 1/2 the number of lattice points on the boundary minus 1. And that's it. That's the entire computation you do. So let's look at it for our star. First, I need to count how many lattice points are on the interior. 18 lattice points in the interior. Now, how many are on the boundary? $19. And if we want to figure out what this is, let's see, this is 18 plus 9.5 minus 1. So this is 26.5. So for our funky star, the area is 26.5. Okay, so Pick's theorem, this is amazing, right? We did not have to compute any A, B, sine, C kind of triangle areas. We did not have to cut this up at all. We just had to do a bunch of counting, divide a number by 2, and then simple arithmetic. Pretty powerful. It relies entirely on the fact that I've drawn a lattice polygon. If my points were not at lattice points, if my corners were elsewhere in the plane, this would not work. Now, how do you prove this? Well, the proof is sort of complicated. There are many steps, but I want to walk through the first step with you here. And the first step proves the result, proves Pick's theorem for a very special kind of rectangle. So rectangles are already nice shapes. Lattice rectangles even nicer. But I want to make sure I'm looking at lattice rectangles where the sides are horizontal and vertical. Nothing skew, just horizontal and vertical. So let's prove that. Let's say this is my lattice rectangle R. So 4 corners, each at lattice points. And let's say that the width is X and the height is Y. We know what the area should be, right? The area should be X times Y. But let's check that the right-hand side of Pick's theorem gets the same answer. So I want to begin by finding the number of lattice points on the interior as well as the number of lattice points on the boundary. And let's do the boundary first. Well, if this has length X, then there are actually X plus 1 lattice points along that bottom edge. And similarly, there are Y plus 1 along each vertical edge, but then you'll notice that I've kind of double counted the corners. However, I can partition the lattice points along the boundary to make this a little easier to look at. So I could look at everything after the first one. If there were X plus 1 total, then there are X lattice points right in here. And similarly, there are Y lattice points along that edge. X within there, and Y within here. So if I kind of cut up my boundary in this way, I see that the boundary of the rectangle has 2x plus 2y points in it. Now what about the interior? Well, this is a grid of points. So this is filled with a smaller grid of points. And there were x plus 1 points all the way across total, but as soon as I look just on the interior, there will be x minus 1 points as the width of that rectangle. And on the interior rectangle, there will be y minus 1 points vertically, because I've just got this rectangular grid and I'm ignoring the boundary of it. Thus, in total, the number of points inside my rectangle is x minus 1 times y minus 1. Okay, so now we've got all the data we need. Let's try plugging it into Pick's theorem. Well, if I plug in my interior number plus the number, plus 1/2 the number on the boundary, and subtract 1, when you distribute and FOIL this out, cancel a few terms, what you get is exactly the area we wanted. So there we have it. Pick's theorem works for this special kind of rectangle, a rectangle with horizontal and vertical sides. The next step in the proof would be to show that Pick's theorem works for any right triangle whose legs are horizontal and vertical. I'm not going to do that here, but that's the next step, and then you would proceed from there. You would start looking at skew shapes. So the proof of Pick's theorem has these different pieces. It's maybe a little more cumbersome than you might like for some statement that's this beautiful. But what I want to do now is focus on some corollaries, some really kind of interesting things that happen. So look back at Pick's theorem. Remember, this is true for any lattice polygon P. Lattice polygon meaning the points all have integer coordinates. Well, what kind of numbers can these be? I mean, if you think about area in the plane, the area might be a very, irrational number. It might be irrational. It might be kind of a messy fraction. It can be all kinds of unpleasant things. But what about for lattice polygons? The number of interior points of the polygon, well, that's always an integer. I mean, I suppose it could be 0, but that is still an integer. The number of boundary points, that's also an integer. You know how many points are in the boundary. Well, maybe there are 12. Maybe there are 37. There are not square root of 10. So these numbers, the I of P and the B of P, are always integers, which tells you that for any lattice polygon, the area of it will always be either an integer or an integer plus 0.5, right? Because you might get an extra lonely 1/2 from the 1/2 B of P, which means, kind of put more generally, the area of any lattice polygon is always 1/2 of an integer. It might be 1/2 of an even integer, it might be 1/2 of an odd integer, but it's always 1/2 of an integer. Already that's impressive. I mean, somehow lattice polygons, even when you draw kind of crazy ones with these weird angles going on, they always have this incredible property about their areas and the type of area, the type of number that you can get. So now I want to ask one more question. Here I drew this really funky star, but what kinds of shapes could you draw as lattice polygons? So I want to think about equilateral triangles. That's a triangle where all the sides have the same length. I want to know if we can draw an equilateral triangle as a lattice polygon. Let's say you can. Let's say that's the equilateral triangle. Maybe one of the sides is horizontal, but maybe it's skew. Let's use every advantage we can. Well, remember that if an equilateral triangle has side S, then the area is S squared root 3 over 4. S squared root 3 over 4. So if this is a lattice triangle, that means these 3 points are lattice points. And I could draw a right triangle here using another lattice point. Now let's see. If these are two lattice points, then the distance between them, that horizontal distance, is an integer. I just subtract their x coordinates, so maybe it's the integer x. Similarly, that vertical distance is also an integer, y. And remember, the side length of my equilateral triangle is s, and I have the Pythagorean theorem. X squared plus y squared equals s squared. Well, in fact, that has nothing to do with lattice polygons. That's just a feature of right triangles. But because this is on a lattice, I know x and y are integers. So x squared is an integer, y squared is an integer. Their sum is an integer, which tells me if this is drawn on a lattice, s squared, x squared plus y squared, s squared must be an integer. Okay. Well, think about what happens to this number then. S squared, some integer, divided by 4, okay, might be an integer still, might be half an integer, might be a quarter of an integer. S squared divided by 4 times root 3. That will never be an integer. It will never be an integer plus 0.5. The root 3 throws us off. It's irrational. Now what's the point of that? Well, look back at this previous corollary. The corollary said that the area of any lattice polygon is always 1/2 of an integer. And I've just shown you that if I were able to draw an equilateral triangle in a lattice with lattice points, its area would never have that property. In other words, it is impossible to draw an equilateral triangle as a lattice polygon. Let's say it can never be drawn. With lattice point vertices. So all of this comes from Pick's theorem. Pick's theorem, this incredibly simple to state and simple to compute result. You draw a lattice polygon, I know its area as soon as I have counted up 2 numbers. Much simpler than a generic polygon drawn in the plane. And then we can draw some pretty neat conclusions from it, including what kinds of areas you might have and what kinds of shapes you can draw as a lattice polygon. Thank you very much.